Hello everyone, and welcome to Calculus 1. So this video and this series of videos will approximate what I would ordinarily be presenting to a classroom. Um, Obviously, the big difference is that there will not be the interaction that I ordinarily have with students. And so, you will have to send me all your questions by email or attend my office hours, online office hours, and ask questions then. So you still have the opportunity to ask me questions, and I encourage that. Um, Unfortunately, you won't have that opportunity while watching these videos. Just make a note of any questions you have, and then just send them my way. Um, so 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 I guess we'll get started. Calculus. So first of all, where did it come from? So right, I'm by no means an expert on the history of calculus, but I can just give you sort of the basics. So it came from all over. It started in Greece, of course, and India, and the Middle East, and China. And probably a few other places. This was a long time ago, thousands of years ago, and it was sort of bit by bit, piece by piece. There were all these disparate ideas about either summations for integral calculus. In Greece they had the method of exhaustion to calculate the area of a circle, and that was, at least to approximate it. And so that's called the method of exhaustion, which again paved the way for integral calculus, hundreds of years later. And so, yeah, around 1500, 1600 in Europe, you had Cavalieri and Fermat and a few others that's sort of put some more ideas together. Of course, then Sir Isaac Newton and Gottfried von Leibniz, Wilhelm Leibniz. So these are the two people that are credited with, inventing calculus. In particular because they developed the ideas more rigorously, and essentially the full apparatus of the two branches of calculus, which are differential calculus and integral calculus. And so Newton and Leibniz sort of put them both together and really explained the relationship between them. And so and just made it much more useful. In particular, Newton used it to explain the orbits of the planets around the sun. And those the orbits of planets were known even before Newton. Most notably, they were mathematically described by Johannes Kepler, and then Newton sort of used his law of gravitation to actually explain why the orbits were what they were. Notably, they were in the shape of an ellipse, and that includes the orbit of the Earth around the Sun, and so on. But yes, so Newton and Leibniz sort of put everything together, came up with the full full machinery that we're going to study here. We're going to study both differential and integral calculus in this course. And then later, all these ideas were made much more rigorous by Cauchy and Euler and Weierstrass and many others that I'm forgetting. Well, there's just too many to mention here, but these are some of the players that made it a full rigorous branch of mathematics, and in particular proved a lot of things that Newton and Leibniz did sort of took for granted. Anyways, so that's where it came from, in a nutshell. So what is it, right? What is calculus? Well, I'm sure you're aware that it's a branch of mathematics, and probably the most succinct way to describe it is that it's sort of a mathematical description of continuous change. Description, of just change, and in particular, continuous change, if that even makes sense. So anything that's changing either over time or with respect to some other quantity, usually you need calculus to describe that, right? And in particular, how fast things change, how fast various quantities will change. And one example of this is motion, right? Things are in constant motion, things are moving all the time. And, how fast things are moving. So in particular, you might say speed is the rate of change of your distance, or velocity is the rate of change of position. And there is a slight difference between speed and velocity. Most people just use those interchangeably, but in math and physics, we need to be a little bit more precise, right? So distance is a positive quantity, right? The distance between any 2 points, say point A and point B, right? The distance between them is always just a positive number. And so speed will always be a positive number, right? Positive. Sorry. Sometimes I'm a little sloppy here. So position is just where you are in relation to some, origin, to some point of reference, right? So, if you're at 0, right, then your position could be 0. If you move to the right, usually that's considered positive. And if you move to the left, that's considered negative. So velocity is how quickly your position is changing, either going to the right or going to the left. So going to the right, you'd have a positive velocity. To the left, you'd have a negative velocity. So velocity could be positive or negative, right? Or 0, obviously. But speed is always positive, right? And again, we'll get into this a little more specifically later. But this is one example of how things change. In this case, how distance or position is changing over time. And it's again how things are changing is kind of a different question. So I want to go back quite a ways to ancient Greece when Zeno came up with this idea, or several ideas, several paradoxes, basically claiming that motion is impossible, right? So one of those paradoxes goes like this, right? So you want to, right? You're at point A, and you want to go to point B, right? So how can you get there? Well, let's just take the simplest path. You're just going in a straight line to get from point A to point B, right? And let's suppose the distance between point A and point B is, let's just make it 1 mile. Well, to get from point A to point B, right, you have to get halfway in between, right? And you can call this, point C if you like. And so that would be about a half a mile from point A, right? So to get to point B, you have to get to point C first. And then to get to point C, from point A to point C, well, you have to get halfway there as well. So there's another halfway point between A and C. You can call it D if you like. But to get to D, you have to get halfway there, to point E. So you see where this is going, right? To get to point E, you have to get to point F, which is halfway to point E. So you can keep going. You just divide this up into further and further halves. So if I zoom in on point A here, right, if this is point A, point Z might be way over here, right? And then, well, we're running out of letters, so you can say, point, ZA, and then ZB, and then ZC, and so on. And then you blow that up, and then there's going to be, if this is point, say, ZZZ, then you got to get halfway there as well. So ZZZA. Right? And so there's no end to this. There's always going to be another point that's halfway there. Right? So to get from any points to any point, to get from point A to point B, you first have to get halfway there, and that takes a certain amount of time. But then to get halfway there, that takes another certain amount of time. And so on, right? So it should take, essentially, forever, an infinite amount of time to get anywhere. Right? So that's the paradox, right? Basically that you can't get anywhere. That motion is completely impossible. Right? To get from any point to any other point will take forever. Take an infinite amount of time. Okay, so obviously that's ridiculous. Things are moving all the time, right? I can move my pen or my stylus or whatever you call it, right? And so things are moving, right? Motion is clearly not impossible. Just look around us, right? Things are moving all the time. But then how do you explain this, right? If it takes an infinite number of steps to get anywhere, how does that happen, right? So unfortunately, to get the full answer to that, you'll have to wait till calculus, the second semester, calculus 2. But if you want the spoiler, sure, you're adding up an infinite number of numbers here, right? You're adding up, one, right? So 1/2 plus 1/4 plus 1/8 and so on. And it keeps going forever. So there's an infinite supply of these numbers, but each of these numbers gets smaller and smaller, right? And some of them are so small that they might as well be 0. So eventually you're adding up things that are almost 0. And so even though you're adding up an infinite number of numbers, somehow you end up with a finite number. In fact, you end up with 1, right? Which is the 1 mile that we had from point A to point B. So Zeno, right, could not comprehend that if you add up an infinite number of numbers that you can possibly get something that's not infinite. Right. So that's the idea, right? So yeah, obviously motion is possible, and it's this idea of dividing this line up into smaller and smaller segments, right? And so that gives us the idea of a limit. So we will learn very shortly what a limit is and how to calculate limits. But what's going to be helpful is this idea that whenever you have any line segment, right, you can get as close as you want to point A, right? You can get closer and closer to point A without ever actually getting there, right? So, right, so you can get, 1/10 of the way there, and then 1/100th, and then 1/1000th, And I'm obviously exaggerating this a little bit, right? So no matter how close you are to point A, to your beginning point, you can always get closer, right? Right, and the same works the other way, right? If you manage to get halfway there, well, then you still have to get halfway there, right? And then you have to get halfway there and so on, right? So you can get as close as you want, but according to Zeno, you'll never get there because you still always have more to go, right? Yeah, now eventually you do get there, and that's the idea of a limit. But just realize that, right, you can get as close as you want. You can make these numbers as small as you want, right? 0.1, 0.01, 0.001, 0.0001, and so on. So these are the decimal versions of 1/10, right? 1/100th, 1/1000th, 1/10,000th, and just keep adding zeros, right? And you can get closer and closer. So we will deal with this idea very shortly. But for now, I think we should just review some concepts that I'm sure most of you are familiar with, but it really doesn't hurt to review them, because if you forgot, or if it's been a while, right, that could make going forward a bit tricky. So I'm going to review some concepts very quickly here in this first video, and then we'll do some more examples about the distinction between things that we can calculate using algebra and then things that will require using calculus. Okay, so that's most of the exercises that you'll get in this first section. But first, a quick review. Right, so I think first we should talk about lines. Right. And in particular, you have your two significant lines here, the x and y axes, right? Right, and so you should know how to graph a line and how to describe a line as an equation. So the two main representations of lines in the xy plane, right? So this is the xy plane, or the Cartesian plane, right? One way is just ax plus by equals c, or yeah, this book likes to use ax plus by, say minus c equals 0, effectively the same thing. So a, b, and c are just numbers, or real numbers. And one thing you can't have is a and b both be zeros. So a and b are not 0. Right. One of them could be 0, but not both. And the other way is the usual y equals mx plus b. Right. So here m and b are numbers, real numbers, right? And these have a significance, so you probably remember m to be the slope of the line. Right? Informally, that's just rise over run. Right? So if you have 2 points on the line, so I'll pick this point here. This will be x1, y1. And then another point way over here will have coordinates x2, y2. So when you connect the 2 points, I missed a little bit with the line between them, the difference in the y's divided by the difference in the x's, right? So we usually call this delta y, and it just means y2 minus y1. And then this distance here will be delta x, which is just x2 minus x1. So the rise is delta y, the run is delta x, and this is the familiar y2 minus y1 over x2 minus x1. Or at least I hope it's familiar. If it's not, well, then, luckily there's a short chapter in the book that will help you, review that. I think it's chapter P for preparation. So it's a good review chapter. It's if you're having trouble with things like slope, right? And B is just the y-intercept, or specifically it's the point 0b on the graph. This is the y-intercept. So a line is completely specified by its slope and its y-intercept. On this graph, the y-intercept is right about here. So that's 0 and b. Sorry, 0. So x is 0, y is b, right? And of course, there's also an x-intercept right here. I don't know what letter to give it. Maybe A, 0. So that would be your x-intercept. And 0b would be your y-intercept. Right. Completely unrelated to capital A and B. Right. So nothing having to do with this A and B here in this version of the equation of a line. Okay, so that's lines, right? Another important concept is functions. Again, you should know what a function is, right? It's usually you think of it like this. Y equals f of x, and you know that this is not f times x, right? Even though we typically do use parentheses to multiply. So if I have 3 parentheses 7, you would calculate that as 21, 3 times 7, right? But f is not a number, right? F is just the name of the function, right? So f is just the name, right? It's a label that we use to denote a function. Right? So for example, f of x could be, x squared minus 3x plus 2. Right? So this is an example of a quadratic function. Right? And one way to think of a function is it's an operation. So you have a function f, and it takes a number x as the input, right? And then the number y would be the output, right? So you have an input x and then an output y, right? And so for this particular function, if the input is, let's say it's x equals 5, again, I just pulled that out of a hat, how would you calculate y? Well, right, so you put 5 into the function and calculate what comes out, right? In this case, it's f evaluated at 5, or you can say f of 5, but please don't say f times 5 because that's not what this is. Right? It's not f times x, not f times 5. It's f evaluated at 5, right? So replacing x with 5, you get 5 squared minus 3 times 5 plus 2. Or 25 minus 15 is 10, 10 plus 2 is 12, so then y is 12, right? So then the output, if the input is 5, the output is 12, right? Right. And the set of all inputs, right? So the set of all inputs is what we call the domain. And then the set of all outputs, the set of all numbers coming out, that's called the range. Actually, it's the codomain, but we're not going to get into that distinction. So we remember domain and range, and so that's good enough for our purposes. Okay, so since I'm out of space, I'm just going to start over with a clean slate. Okay, so we're talking about functions, and we still have this example here. And in particular, you should know that, right, again, x being from the domain is the input to the function, and then what comes out is the y that you calculate as f evaluated at x, right? And of course, x will usually be a number, but it doesn't have to be, right? So I can stick into the function a letter, like a. And all that means is you replace x with a. So you get a squared minus 3a plus 2. Right? You can stick in another letter like w. And then this is the corresponding output. right? But you can stick in something more complicated, like an expression. Suppose I have, 2z minus 3. So what would f evaluated at 2z minus 3 be? Again, everywhere you see an x, you change it to 2z minus 3. Right, that's all it is. And of course, you should know how to multiply all this out, so I'll do that quickly. You get 4z squared minus 12z plus 9, and then minus 6z plus 9 again, plus 2. So you combine like terms, you get 4z squared minus 18 times z plus, let's see, 18 plus 2 is 20. Okay, so that's the corresponding expression that you get when x is just 2 times z minus 3. Okay, so yeah, this, you should be very comfortable with this. We already talked about domain and range, right? You should also be familiar with the difference quotient. Right. So this is called the difference quotient. If I can squeeze that in here. Right. And you should know how to calculate it. In fact, we'll use the same function, x squared minus 3x plus 2. So for starters, what is this f of x plus delta x? It just means you replace x, right? All these x's with x plus delta x. So it's, instead of x squared, it's x plus delta x squared minus 3 times, again, x plus delta x plus 2. Now there's no x with the 2, right? So yeah, you just leave the 2 alone, right? Right. So that's usually the first thing you have to calculate when you're calculating the difference quotient. It's just this. Plus 2, right? And then you still have to subtract the f of x. So f of x, of course, was just x squared minus 3x plus 2. And this is all divided by delta x. Okay, so just to make this clear, this here is f of x plus delta x, and this is just f of x, and you just subtract them, take the difference, right? Okay, so just expand all this out. You should get x squared plus 2x delta x plus delta x squared minus 3x minus 3 delta x plus 2. And then don't forget to distribute the minus sign here. So we get minus x squared plus 3x minus 2. All divided by delta x. Right. And please, I hope you're not wondering, where did I get this 2x delta x from? Because I thought it was just x squared plus delta x. So yeah, remember when you square a binomial, I'll do that up here. If you have a plus b squared, please do not write a squared plus b squared, because that's wrong. If you make that mistake over and over, you're going to have a problem, right? This is going to be a big mistake going forward. So remember what a plus b squared means. When you square something, what are you doing? You're multiplying it by itself. So it's a plus b times a plus b. And now you should know what to do, right? Remember the 4-letter word here, FOIL? First is the first two terms here, a and a. So a times a is a squared. And then the O stands for the outer terms, a times b. The I stands for the inner terms, which is b times a. But remember, b times a is also a times b. right? Doesn't matter what order you multiply. 3 times 2, 2 times 3, same thing. And then the last two terms is the b and the b. So b times b is b squared. Right? So now you know where the 2x delta x comes from. ab plus ab is just 2ab. Okay. So this is the last time I'm going to explain this. So make sure you understand that a plus b, the quantity squared, is not a squared plus b squared. Right? You're missing the all-important 2ab. So that's the 2x delta x down here, right? Okay, so notice what else happens here, right? We get positive 2 and negative 2. That adds up to 0. We have positive 3x and negative 3x. That also adds up to 0. And we have negative x squared and positive x squared. That also adds up to 0. So the numerator is a lot simpler than it was. It's just 2x times delta x plus delta x squared minus 3 times delta x, all divided by delta x. Right? And now you have two options here. Right? The way I would do this is to notice that in the numerator we have a factor of delta x in the first term, a factor of delta x in the second term, and a factor of delta x in the third term. So I would just factor it out, leaving you with 2x plus delta x minus 3 all over delta x. Right. And now delta x divided by delta x is 1. Is that clear, right? 5 divided by 5 is 1. Right? In fact, anything divided by itself will be 1. Right? As long as this delta x is not 0. And that's going to be important later. So we're assuming that delta x is not 0 here. Right? But as long as it's not 0, then the answer is just 2x plus delta x minus 3. Okay, so that's the difference quotient of the original function. So let me remind you, this is the difference quotient of the function f of x, which was x squared minus 3x plus 2. Right. So yeah, this is a pain to do, but it's something you should remember from your algebra pre-calculus days. Simplifying the difference quotient until you get to something like this. So this is something we're going to do, well, pretty soon. Right? This is something we're going to do again and again. And with even more complicated functions than just a quadratic function. So hopefully this is a good review of functions and finding difference quotients. And of course you can also compose two functions, which is right, composition of functions. And I'm assuming you know how to add functions, subtract functions, multiply them, divide by functions, right? But this is composition, right? So this f of g of x here, this is the definition of the composition, right? This is not f times g. Make sure you're comfortable with that. If I wanted to write f times g, I could write fg of x, or I can write f of x times g of x, right? But not f of g of x, right? So this is f of g of x. Right. Effectively, you're just chaining the two functions together, right? You think of x first going into the function g. What comes out of that, the output of g is g of x. And then you think of the g of x as the input to f. And so the output of f, when the input is g of x, is f of g of x, right? So this is composition. Right. So as a very quick example, suppose f of x is just the function square root of x, and g of x is the function 3x minus 6. then you know how to find f composed with g of x. And you can do this a couple ways. I prefer to think of what does f do to x, right? F takes the square root of x. So what does f do to g of x? It takes the square root of g of x, right? It takes the square root of whatever's inside the parentheses here, right? Now, what's g of x? It's just 3x minus 6. So, right, f of g of x is the square root of 3x minus 6. Right? And of course, you can go the other way. You can take g composed with f of x. So now, what does g do to f? Well, it multiplies it by 3 and then subtracts 6. And what's f of x? It's just the square root of x. So what you get is 3 times the square root of x minus 6. Right? And you can see that that's not the same thing as the square root of 3x minus 6. So, right, in general, of course, f of g of x is not the same as g of f of x. Right, in general. Right. However, you should know when they are the same. So, right, when f of g of x is equal to g of f of x, and in particular, if they're both equal to x, right, you know that f and g are inverse functions. We will talk about that toward the end of the course, but you should know what inverse functions are. Composition, this is something you've done many times before, I would hope. What you might want to do is think about going the other way. What we did here is we took two simple functions, and when you compose them, you get these more complicated functions. So if you have a complicated function, can you decompose it into simpler functions, right? So this is going to be a useful technique later on. Suppose I have a function, let's say h of x, is equal to, let's take the sine of x cubed minus 4x squared plus the square root of x. Okay, so this is a rather complicated function, right? But you can see that you're taking the sine of something, right? The sine of this angle here. So let's call this angle g of x, right? So g of x is just x cubed minus 4x squared plus the square root of x. And what is the function h doing to that? Well, it's taking the sine of that. So we should say that f of x is just the sine of x. Right? So if we think of h as f of g of x, what do we get? We get the sine of g of x, which is the sine of, equals, the sine of x cubed minus 4x squared plus the square root of x, which is what we started with, right? That's your h. Right? So yeah, we decomposed h into two simpler functions. And this is something you're going to do over and over, in many cases without even thinking about it, right? So that's one example. And speaking of sine and cosine, obviously this is trigonometry. So you should know your sines and cosines. You should also know that tangent, right, is just sine divided by cosine. You should know that cotangent is 1 over tangent, the reciprocal of tangent, which is cosine over sine. You should know that secant is 1 over cosine, and cosecant is 1 over sine. Right, so you should know all 6 trig functions, and obviously you should know the basic values on the unit circle. So if we draw the unit circle, you should know all the trig values at 0 degrees or 0 radians, right? Pi over 6 radians, which is 30 degrees, pi over 4 radians, which is 45 degrees, pi over 6, pi over 3 radians. We already did pi over 6, right? So pi over 3 is 60 degrees. Sorry, should be straight up and down here. Right, the North Pole here is pi over 2, or 90 degrees, and so on. I won't go any further, but you should know the values at any multiple of pi over 6 or pi over 4, or pi over 6 or pi over 4. All multiples of those angles. You should know the trig values. And it's in your book. In fact, it's in the front cover if you have a physical version of the book. If you have the e-book, you just look on the second or third page. It should be there. So this is the unit circle. All the angles and the trig values should be there. Okay, so that's as much review of trigonometry as I'm gonna do here. I think one more thing you should know, because on that same sheet there's a whole bunch of formulas, trig identities, and so obviously you should know the reciprocal identities. These are just the definitions of the trig functions. But most of the others you probably don't have to know by heart. One that you might want to know, because it will come up over and over again, is the Pythagorean identity. Sine squared of x plus cosine squared of x is just 1, and that's true for any x, for any real number x, right? But other than that, all the others, if we need them, we can look them up, or I will refer you to them. But this identity here, the Pythagorean identity, comes up quite often, and we will see it over and over again. The others will come up as well, but maybe not enough to warrant memorizing them. In fact, if you took pre-calculus with me or at NCC, you were given a formula sheet for most of those identities, but not these here, not the definitions, right? So these you should know for sure. Okay, so that's trigonometry. Okay, so hopefully that's enough review. If not, I would encourage you to at least look over the chapter P in the book, the review chapter. At least go through some of the exercises in the review section, just to make sure you're all caught up. So this is one of the exercises in the first section here. So let's go through it. The question says to find the distance traveled in 15 seconds by an object traveling at a constant velocity of 20 feet per second. Right. So you should know the relationship between velocity and position. So actually they use the word velocity here, but they could have just as well used the word speed. In fact, I would prefer that they use the word speed. Right? Because remember, velocity can be positive or negative. But here the velocity is positive. And when you're talking about distance will always be positive, right? Right. So I'm going to use the word speed here, right? So hopefully you know what speed is. Right? It's just the distance you travel divided by the amount of time it takes to travel that distance. So speed is just distance divided by time. Right. Or, since we're looking for distance in this case, if you multiply both sides by the time, we get that distance is just speed times time. Right. And in this case, parentheses, here it means multiply, right? Okay. Right. So you should know that, and that's really all you need to answer the question, right? We're looking for the distance. We know the speed is 20 feet per second, and we know the amount of time it takes is 15 seconds, right? So when you multiply 20 times 15, you get 300 feet. Right? Notice that seconds as a unit cancels. Seconds divided by seconds is 1. So this is just 300 feet. so hopefully that was an easy one. But now let's get to a more difficult one. So here the question says to find the distance traveled in 15 seconds, right, same as the last problem, by an object moving with a velocity v, which is given by the function v of t is equal to 20 plus 7 times the cosine of t. Right. So we just talked briefly about cosine, right? So this is a much more difficult problem than the last one, right? In the last one, what allowed us to do this was the fact that the speed was just a number, right? The speed was constant here. It was a constant value. So whatever object this is, it's traveling at 20 feet per second always, right? So it's moving at a constant, right, or uniform speed, uniform velocity. But in number 4 here, the speed is not constant. Okay? So in this case, we cannot find the distance by just multiplying, right, speed times time. Because the speed is not a fixed number here, right? Because the speed is a function of time. Right? So yeah, it's because speed is not constant. Okay? So well, then how can we do this, right? Well, the short answer is we can't do this yet, right? This uses calculus, right, to get the precise answer. Okay? And so, yeah, it's very unlikely that you know how to do this, at least not exactly, unless you've had calculus before, in which case you know what to do, right? So what could we do here? So we're going to think about number 3 in the following way, right? Suppose we were to make a graph. This is going to be, instead of the x-axis, we'll call it t for time. And the vertical axis here will be for speed. So I'll call it v for speed. And let's see, we know the speed was, it's 20 feet per second, and the time, obviously not to scale here, let's say this is 5, 10, 15 seconds. Right? So what you get, if the speed is constant, it's just a horizontal line. And then if we stop at 15 seconds, well, in this case, right, if you multiply 15 times 20, that's just the length times the width. So in other words, the area of this rectangle becomes the distance, right? So we can think of the distance here as being this area and the distance, right? So yeah, in this case, right, the 15 is the length of the rectangle, and 20 is the height or width. I guess I'll call it height in this case. So that might give us this idea of how we might be able to calculate the distance in number 4. So it helps to draw the graph, of course. So this is t. Again, we'll have 5 seconds, 10 seconds, 15 seconds, and so on. And yeah, we could do the same thing here. So 5, 10, 15, 20, 25, and 30. So this is going to be the speed, v. And so on, right? So let's see. So how do we graph this function here? Well, notice that it's just a cosine function. You know, cosine just goes back and forth like this. That's the usual sine and cosine wave. And if t is 0, right, cosine of 0 is 1. So you start out at 20 plus 7, right? 27, I think this is in feet per second, right? 27 feet per second. Right, so that's right about here. Right. And now it gets a little tricky because they didn't multiply this t by, say, a factor of pi, which would have been nice. So we're just going to have to do this the usual way. If we plug in pi over 2, which is about 1.5, right? A little more than 1.5, right? Cosine of pi over 2 is 0, so you just get 20. So let's see, if we approximate this by roughly 1.5, we get to 20. Right. And if we plug in pi, which is about 3.14, now we're at 20 minus 7, which is, 13, if I can add correctly. So 13 would be, let's see, right about here. Right. And so on. So, right, when you get back to 2 pi, that's the same as 0, you're back to 27. And 2 pi is a little more than 6, so we're right about here. Right? So here you get your cosine wave. Let me try to make it as neat as possible here. I know that does not quite look right. And it's a periodic function, right? So it just repeats itself like this. Okay. And where do we want to end up, right? We're going for 15 seconds. I'm trying to do a vertical line, so right about there, right? And so if we're using the same idea here, that the area is the distance, then we just have to find the area of this region in here. So you can see that's going to be a lot more complicated than, say, finding the area of a rectangle, because this is not a rectangle. This is a weird curve that just goes back and forth, right? Right. So obviously we're not going to be able to get this exactly. But one thing you could notice is the following, that because this goes back and forth, it is periodic. If we kind of go right in the middle here, like this, we can see that if we take the area that's above that line, which is, right, v equals 20, so this is, shoot, I forgot to mention that this is 20 here. If we go above that line, we're overcounting the area, but notice that below the line is this region in here, and that looks about the same as this. Just, right, if we take this area and fill it in, where it's like we're filling in the gap, right? And if we take, this area here and fill this in, they should cancel out, right? And then this should fill in here, this should fill in here, and so you can see that by the time you get to 15, well, we can't quite go more than 15 here. So this might be, well, first of all, this might be a little bit off. But remember, we're just estimating here. We're just approximating. And so this is very close to a full rectangle then, which would just be 20 times 15, which is still 300 feet. So it turns out that the distance traveled is not much different than if it was going at a constant speed of 20 feet per second. Right. Now I do have to say that this is a little bit off here because there's the little bit of this gets filled in, but not the whole thing. In other words, there will still be this gap in here. Right. So it looks like it's actually going a little bit more than 300 feet. And I forgot the more precise answer here. So this is only approximately 300 feet. The actual distance is a little bit more than that. And I think as an approximation, I think it's about 304 feet. Or more precisely, 304.55 feet. Okay, so how to get that exactly? Well, you have to wait until the end of the semester. Then we can use calculus to calculate this exactly. But again, as an approximation, 300 feet, you're off by, a few feet, 4.5 feet, which isn't too bad. But again, it just depends on how precise you want the answer. If I wanted a precise answer to say 2 decimal places, then 300 is not good enough, right? We want 304.55 feet. But if we only wanted the answer, say, to the nearest whole number, you'd get, 304, 305 feet. And so the 300 feet is a bit off, but not significantly, right? It's, it's what, about maybe 1.5% error or something. So in the grand scheme of things, a 1.5% error is, not that bad. Well, I guess it depends on, your application and how precise you need to be here. So, okay, so that's distance and speed and time. So at the very least, what you should come away from this is make sure you know that speed is distance divided by time. And while that's true in example 4 as well, it's not really the speed, because the speed is not a constant. But you can say it's the average speed, right? The average speed is what's distance over time. And so the average speed is about 20 feet per second, maybe a little bit faster than that. Yeah, slightly faster than the 20 feet per second. Okay, so yes, average speed is distance over time, and we'll come back to that a little bit later. Incidentally, right, so part of calculus is also calculating areas, right? So it's not just about rates of change. It is also about finding areas, and in particular summations, a continuous sum. So suppose I have a graph of some generic function, f of x, right? And we want to find the area between a and b, the x-axis and the curve, right? In other words, this area in here. Okay, so that's a hard problem, right? That's going to require calculus to do that, right? But one way to think of this is to sort of approximate it with things that we know how to find the area for. In particular, rectangles, right? We know how to find the area of a rectangle as long as we know its width and its height. Right? If we know the width and the height, the area is just the width times the height, right? Okay. So obviously the problem is that this, right, is not a rectangle, not even close, but we could divide it up into little rectangles, right? So something like this. Here's one rectangle. Here's another rectangle. Try that a little bit better here. Right, here's another one. Here's another one. You get the idea, right? And I think I can put in one more here. I'll pretend that's straight. I'm having a hard time drawing this, right? And then this one here, right? So these are all just a bunch of rectangles. And so I can find the area of the first rectangle, right? The second rectangle, the third one, the fourth one, the fifth one, the sixth one, the seventh one, and the eighth one. And so what we get is a pretty good representation of the area, right? Now it's not exact. In particular, you see there are these little gaps in here that are not part of the actual area. So if we add up all these blue rectangles, right, we're going to get an approximate area, but it will still be an underestimate. It'll be less than the true area, right? Because we're not taking into account, say this area, oops. The wrong place here, this area, this, right? So, yep, so we're missing all this red area in here, and that causes the approximate area to be less than what it should be. Okay, right, so this is going to be the idea a little bit later. When we want to calculate areas, we just start with things that we know, in particular rectangles, because we know how to find those areas. And you just divide this up into a series of rectangles, a lot of rectangles, in this case just 8 of them, right? And I've sort of obscured the rectangular part here, but these are just 8 rectangles. And you can imagine if you really want to get a better approximation, a better estimate, maybe you should do more rectangles than just 8. If you do 20 or 50, then these gaps here, right, all these red areas, even though there's more of them, they get smaller and smaller. And so you get a better and better estimate the more rectangles you have. Okay, so that's the idea that we're going to encounter, toward the end of the semester. About halfway through the semester, we'll get to finding areas and then finding sums of those areas, right? So this is just a sum of a bunch of areas of each rectangle, each of which we know how to calculate. And so we're approximating the area under the curve by the areas of all these rectangles. Okay, so I hope at least that helps for now. Okay, so one final example, and this is also from the homework. This is number 8, at least in the 11th edition. Yeah, so if it is for homework, that's fine. You should try it first, right? It's not a difficult problem, but it does involve a lot of concepts that, again, I reviewed earlier, concepts of slope. And if you don't remember slope, then it is a difficult problem. Then it's, So, right. So we have a function, f of x equals 6x minus x squared. Right? So it's a quadratic function. And we have a point on the graph, 2, 8. And, well, you should confirm that, right, that point is on the graph. If I plug in x equals 2, I get 12 minus 4, which is indeed 8. So that tells me that the point, 2, 8, is on the graph, right? And so part A, we should obviously graph the function. So let's do that right now. And I'm just debating about how big to make it. I do need a rather big graph here, although that's going to be a little sloppy. Okay, so this is 1, 2, 3. And again, I realize that I got to go all the way up to 8 at least. In fact, I think I have to go up to 9. All right, so we'll make this 1, 2, 3, 4, 5, 6, 7, 8, 9, and we'll make it 10. Okay. So, right, and then for x, this is just 1, 2, and 3. Okay, so hopefully you know how to graph the function. We'll just plug in, can I do this in red here? I'll do it in green. Right, so when x is 0, y is 0, right? And when x is 1, we get 5, right? So 1, 2, 3, 4, 5. Right about there. When x is 2, we already did that, we get 8. So 5, 6, 7, 8. And maybe I should label these just to make it clear. So 1, 5, 2, 8. And then when x is 3, we get 18 minus 9, which is 9. So this will be the point 3, 9. And then, of course, the graph keeps going. So this is our parabola here. Let me try to do a slightly better job than that. Okay. And I think 3, 9 is the vertex, so it actually decreases from that point on. Okay, so this is a very sloppy graph of f of x equals 6x minus x squared. So that's one thing we wanted to do. They also want to graph the secant lines passing through the point 2,8. And for these 3 points here, 3, 2.5, and 1.5. And I'm not going to do the 3. So you can do that if you want. I'm going to do the 2.5 and the 1.5. Okay, so maybe we should figure out, right, what is f of 2.5? Well, it's 6 times 2.5 minus 2.5 squared. So just put that in your calculator. And I get 8.75, or 8 3/4. All right. So on the graph, that's going to be roughly right here. So 2.5, it's supposed to be 5, and then 8.75. So that's the red point. And then for 1.5, I'll do that in yellow. So this is 6 times 1.5 minus 1.5 squared. And I think that's 6.75. Right. So yep, 1.5 right about here. Here was the 2.5 from earlier. And then this should be, let's see, 5, 6, 6 3/4. So that looks about right. It looks pretty close. So this is the point 1.5 for x, and then 6.75 for y. All right, now what is a secant line? So first of all, we call it a secant line. As far as I know, has nothing to do with secant, the secant function from trigonometry. It's just a line that passes through 2 points on the graph. So obviously, when you have 2 points on the graph of a function, the line between those 2 points is called a secant line. Okay. For reasons that I'm not quite sure what that has to do with the secant function, 1 over a cosine. I don't think it has anything to do with that, right? But then you have this other idea, which we're going to encounter again and again. So suppose you have only 1 point on the graph, like say this point right here, and if you want to draw the line that just touches that 1 point, but no other point, then we call that a tangent line. Okay, so a secant line passes through 2 points of the graph. The tangent line passes through only 1 point. So it passes through 1 point. And I have to add the word locally, because a tangent line could cross the graph at more than 1 point. Why? Well, let's say the graph did this. So here, the tangent line crosses the graph over here. Right? But that does not make it a secant line, because locally just means near the point where you have the tangent line. So drawing this little circle here, in that neighborhood, the graph only crosses once. Actually, it only touches the graph once. So the tangent line only touches once nearby. It may cross elsewhere, but further away, right? The point about a secant line is a secant line will cross at 2 points for sure, and they don't have to be that far away, right? So in other words, if I can have a secant line that passes through this point, and these are actually very, very close by. So not a tangent line, because it crosses at 2 points. A tangent line only touches the graph just once nearby. Okay, so that's secant line and tangent line. But right now we just want to graph the secant lines. So let's start with 2.5. So that's going to be a line that crosses here and here. And that line will look something like this. I think I missed a little bit here. Let's try that again. So the green point and the red point. So that's the secant line passing through. Maybe I should label these. How about A, B, and C? So the red point is B. And then the yellow point will be C. Right? So we have the secant line from A to B, and then we have another secant line from C to A. So that's going to be that line there. Right? So those are the graphs of the secant lines passing through those points. And like I said, I'm not going to do the line for x equals 3. You could do that one by yourself if you want. Right. So part B, now we want to find the slope of each line, the red line and the yellow line. Okay, so let's start with the red line. So part B, okay, so you know the difference between a secant line and a tangent line. Okay, so we want the slope of line, say AB. And that's right, so it's passing through 2 points. One point is 2, 8, that's point A, right? And the other point is point B, which has coordinates 2.5 and 8.75. Okay. So you should know how to find slope, right? M for slope, right? Rise over run. We just did that maybe half hour ago, right? y2 minus y1 over x2 minus x1, right? So of course we're giving you x1 and y1 and x2 and y2. So we just plug in the numbers now. y2 is 8.75. y1 is 8. x2 is 2.5. And x1 is 2. So when you subtract, you get 0.75 divided by 0.5. And you can either put that in your calculator or, let's see, this is essentially 75 over 50. I think this is just 3 over 2, right? Or 1.5. Now, if the red line does not look like, remember, a slope of 1 is like 45 degrees, right? So if that's a slope of 1, the red line looks like it's a little less than that. So how can it be 1.5? Because it looks like it's more like, 1/2 or something, or 0.5. So remember, look at the scale here, right? Remember I changed the scale? So, right, so this is 1, 2, 3, 4, 5, 6, and so on. So you can see because this oops, oh, sorry, I missed one, 9. So this is 9, that's 10, right? Yeah, so the y scale here is squashed significantly. So, right, so if I were to do a proper graph, it would look more like this, right? And then the red line would probably look like this, and the yellow line will look like this. And so you can see that they will be a lot steeper than they were in my graph, right? And you have to be careful when you graph things on your calculator. There is an inherent distortion because the screen is, rectangular. It's not a perfect square. So you will get that effect in your calculators unless you change the scale. Okay. So anyways, that's one answer, right? The slope of the red line here is either 3 over 2 or 1.5. What about the slope of the yellow line? Right? So we're going to do the same thing, same formula here. So we want the slope of the line C to A. Right? So passing through C and A. So the point C has coordinates 1.5, 6.75. And point A again has coordinates 2 and 8. So same formula, y2 minus y1 over x2 minus x1. In this case, I can consider x1 to be 1.5, y1 to be 6.75, x2 is 2, and y2 is 8. So plugging in those numbers, we just get 8 minus 6.75 divided by 2 minus 1.5. So I think we get 1.25 divided by 0.5, which I think is 5 over 2, or 2.5, 2.5. Okay. So yeah, that's the slope of the yellow line. Again, it looks like, from the graph, it looks like it's still less than 1. But if you look at the proper graph that's not distorted, you can see that this line looks like it has a much bigger slope, 2.5, right? And then the red line has a slope of, say 1.5. Okay, so that's part B. Part C, using the results of part B, which we just did, estimate, right? So estimate the slope of the line, the tangent line to the graph at the point 2,8. So at point A here, and I'm running out of colors, so maybe I'll use a blue line here. Estimate the slope at this point here, at point A. Right, so the slope of the graph is the slope of the tangent line. So it's going to be kind of hard to draw a tangent line, but it's going to look something like this. Right. So you can see it's going to be somewhere between the red and the yellow lines. And maybe in this picture it'll be a little bit better. Right. It's the blue line. Right. So what's the slope of the blue line? Right. And just to estimate. Well, so we know it's somewhere between 1.5 and 2.5. So it's bigger than 1.5. It's less than 2.5. So as a guess, you could anywhere between 1.5 and 2.5. Right? You can split the difference and just say it's exactly halfway between. You can say it's 2. Right? But, if you guessed 1.9, right, or 2.17, those are reasonable guesses as well. Right? It's really hard to tell just looking at the graph, of course. But anything between 1.5 and 2.5 would be a good guess. Okay, would be a good estimate. Right. As a spoiler, it turns out to be exactly 2. So I'll say T for tangent line here. It does turn out to be 2 exactly. But how do we know that for sure? How do we know it's not 1.9? Right, or maybe 2.003, something close to 2, but not exactly 2. Right, so that would be a good guess as well. But it turned out to be exactly 2, and we'll learn how to get that very, very soon, right, within the next week or two. Okay. Yeah. So describe how to improve the approximation. Well, you kind of have to zoom in on this point here, right? And if I zoomed in, if this is point A, and the graph, looked like this, right? We're looking for the slope of the tangent line at that point, right? And remember, way down here is point B, so here's the secant line from B to A. Oh, I'm sorry, this was point C. Right, B was the red point way over here. Gotta make it red. Right, So that's point B. So here's the secant line from A to B, right? And the blue line, again, is in between. So this was 1.5. And then for the yellow line, the slope was 2.5. So, yeah. So it's got to be somewhere between. So how to improve the slope, how to get a better estimate than anything between 1.5 and 2.5, how about instead of using point C or B, maybe let's use a point D, which is very close to A. Right, so remember, point A, I believe, was 2.8. So for point D, instead of using 2.5, maybe just use x equals 2.1. Okay, so what's y when x is 2.1? So what's f of 2.1? So 6 times 2.1 minus 2.1 squared. Again, plug that into your calculator. And I get 8.19. So that's the y-coordinate here. And now use that as your x1, y1. Or, yeah, either way, x1, y1. And x2, y2 will still be 2 and 8, respectively, right? So now to get the slope, same y2 minus y1 over x2 minus x1. Again, you got to know that formula for slope, right? So it's 8.19. Oh, I got it backwards. It's 8 minus 8.19, right, over 2 minus 2.1. So I think we get negative 0.81 divided by, sorry, it's negative 0.19. I don't know what I'm thinking. Yeah, I should just use my calculator, right? So negative 0.19 divided by negative 0.1, right? So that turns out to be positive 1.9, right? Yeah, the slope should be positive, right? So, yeah, you notice that it didn't matter which point I called x1, y1, and which point I called x2, y2. If you switch them, you'll just get a positive divided by positive instead of a negative divided by negative, right? Right, so 1.9. Well, it's a lot better than 1.5 or 2.5. But even still, it's not exact, right? The 1.9 is still the slope of a secant line, right? Because it's passing through 2 points, right? Point D and point A, right? But it's a much better approximation. It's closer to the actual value. Again, we know the actual value is, of the tangent line is exactly 2. Why is that? We don't know yet. But we will get to that shortly. Right. So this is, I think, a good introduction to secant lines and tangent lines. And very shortly, if you're wondering, why do we care about tangent lines? Why do we care about secant lines? This we'll get to when we talk about velocity again. But very briefly, if this function here represented distance or position, right? So we'll say that f of x is your position, right? Then what we've been calculating, right? The slope of the secant line is just your difference in positions, right? So this is the distance you traveled. Well, okay, distance could be positive or negative, right? Maybe we should call this the displacement that you travel. It's the difference between the 2 points, right? And then the x's represent time here. So it's the time that it took to go that distance. Right? So this is your average velocity. Right? Average velocity. So this is why the slope of the secant line is important. If you want to calculate average velocity, you're calculating, right, the slope of the secant line. Right. So what's going to be important is to calculate what's called the instantaneous velocity. Right, this is your velocity at a given moment in time. I can spell velocity at a moment in time. Right? In other words, at a specific value of t. Right? So let's say at time t is equal to 2. Right? Could be 2 seconds, 2 hours. We didn't give units here, so right. So if we give units, you should include units in your answer. But let's just say t equals 2, right? So what is the velocity at time t equals 2? Right. Right. So this is a calculus question. This is one we really can't answer yet. Right. Right. So this is the same as the slope of the tangent line. At x equals 2. Okay? So why is that a calculus problem? Why is that a hard problem? So again, you have your curve, right? This is, in this case, f of x, or it probably would be better to use s for distance and t for time. Right? So this is the time axis. This is the position axis, or s. So we use s for position rather than p, or d, right? We don't like using d for distance. We'll use s as well. Right? So if this is the graph, and you want the rate of change at time t equals 2, then you want the slope of the tangent line at that point. Okay, so the slope of this line will be your speed, or your instantaneous velocity. Well, let's try to calculate that, right? So remember, we had the position as a function. It was just 6x minus x squared. Just had to remind myself of that, right? So let's say s of t is 6 times t minus t squared, right? Same function. Same function. Whether you call them t's or x's, or f or s, same idea. And we already know your position at time t equals 2. That's 8, right? So 8 meters, 8 feet, 8 miles, whatever the units were, right? So that's just the y-coordinate here, right? Y is 8. So that's the 0.28. Right, so how do we calculate the slope of that line? Well, the only way we know how to calculate the slope of a line so far is to use the slope formula, right? Now, in this case, it's going to be S2 minus S1 over T2 minus T1. But same numbers, right? So we have our T1 and our S1. T is 2, right? And S is 8. But remember, this is a tangent line. Any other point nearby that's on the graph is not going to be the same as the point on the line. So here's the issue. We don't know any other point on the line here. Right? All these other points on the line are not part of the graph. They're not part of this blue curve here, right? So we don't know the coordinates of these points, right? We could guess, we can estimate, but we don't know them exactly. We only know points on the curve exactly, but those points are not on the line. Right? At least not locally, right? Not by definition, right? A tangent line only touches the graph once nearby. Okay, so the only thing we can do is, right, use the same t and s for t2 and s2. In other words, they're both equal to 2 and 8, right? So s2 is equal to 8 and s1 is equal to 8. t2 is equal to 2. and t1 is equal to 2. So 8 minus 8 is 0, and 2 minus 2 is 0. So the slope, right, of the tangent line this is also your instantaneous velocity. We calculated this to be 0 divided by 0. Well, that doesn't help whatsoever. 0 divided by 0 is not even a number. It's not a number at all. It's meaningless. Right? Think about that. What is 0 divided by 0? Right? It could be anything. Right? If you think it's what did we say it was, right? We said it was exactly 2. Right? So let's say it's equal to 2. Right? Is that correct? Well, how do you check a division? You multiply, right? 0 times 2 is equal to 0. So yeah, that works. But I would say 0 divided by 0 is equal to 173. Am I wrong? Well, let me check. If I take 0 times 173, yeah, I get 0. So I'm not wrong. I just checked it. It works. If you think the answer is, 7.9, well, you're not wrong either. 0 times 7.9, right, is still 0. The point is anything times 0 is 0. Okay? So whenever you see 0 divided by 0, you know something went horribly wrong, because that cannot be the answer. Okay? In fact, 0 divided by 0 is what we call an indeterminate form. Means we can't determine it, right? We don't know what it is. It could be anything. And so it's useless to us, right? 0 divided by 0 is a useless thing. I don't even, right? You can't even call it a number, right? It's not a number, right? Or if you think it's a number, the problem is it could be any number. So if the question is, how fast are you going? And the answer is, I don't know. It could be anything, right? I could be going 2 miles an hour. I could be going at the speed of light, right? I could be going 186,000 miles per second. Or anything in between. Then that doesn't really answer the question, how fast you're going, right? If you don't know, then just say, I don't know how fast I'm going, right? So that's the issue, right? If you try to calculate the instantaneous velocity or the slope of the tangent line by using the usual slope formula, the formula that we already know, you're not going to get a good answer. You're not going to get any answer, right? You're going to get anything. Could be anything. So that's a pointless answer, right? So yeah, we can calculate average velocity or the slope of a secant line. We did that here twice, right? Once with the red line and once with the yellow line. But we cannot calculate the slope of a tangent line just using the formula here, just using this. Right? Oh, we estimated it. We got a good approximation. In fact, we got, being somewhere between 1.5 and 2.5 is, it's a reasonable estimate. But why is it exactly 2, right? Why does it have to be exactly halfway between? In fact, it didn't have to be. That's just a coincidence. Right? It has to do with the fact that this is a quadratic function. But for most functions, that's not going to happen. So don't count on that happening. This is just happens to be a nice problem with a nice number as the answer. Yeah. So yeah, the original question, to estimate the slope of the tangent line, it's about 2. Right? It's approximately 2. Right. All we know is that it's somewhere between 1.5, right, and 2.5. That's the best we can do. So even if you said 1.6, right, or 2.3, you're not wrong. It's between 1.5 and 2.5. That's sort of the best we can do here. Right. So it is about 2. I mean, it is exactly 2, but we won't know that for a while until we can calculate the slope of a tangent line. But in order to do that, and again, that's going to come in the next chapter, right? But for now, to do that, we need the idea of a limit, right? So that's going to be the subject of the next section, which is the next video, right? So hopefully this is enough to go on to be able to do the problems in the first section. So at least I hope this was a reasonable introduction to calculus, right? It's giving you just the basics for now, and we will get into the details soon enough. So I hope this helps.